about 2/3 of the way through this mid-deck level now. And as I said, we elected to use high-performance lightweight concrete to help guarantee the service life and to achieve the performance opening and closing. They had to pump water in and out of it to lift it up and down and set it on the bottom. So of course the challenges is that this is a brinish area. It's connected to the Gulf of Mexico, so there's a high potential for corrosion. Of course there's wetting and drying problems. There's potential for barge impacts, so there's because the vessels are going by it through the pass, it could butt up against it. There's also, it doesn't snow very often in Louisiana, but I've been there when it was snowing, so it does happen once every 20 years or so. It's the coldest tropical climate in the world. So in any event, here are some of the challenges for making the high performance concrete. We wanted to have low permeability to resist the chloride penetration. We wanted to have high strength to resist impact. We wanted to have high workability because of all the reinforcing steel in there. And we wanted to keep it lightweight to help it float and reduce its draft, which allowed water to flow under it when it was setting down, which reduced the mooring forces on it. So here are some of the characteristics of comparing high-performance lightweight concrete versus high-performance standard weight concrete versus normal standard weight concrete versus, well, this is normal lightweight concrete and normal standard weight. So you can see that it's, in some ways, it's the best of all worlds except for cost. And since it was a small component, the costs were justified compared to the other options that were available at the time. Certainly Caltrans uses lightweight concrete periodically for bridge decks to get the inertia down for seismic loading, but here it was for buoyancy to reduce the draft. But fortunately it gave us also better service life by decreasing permeability, and we had very good strengths on it, so we have this issue about service life that Eric was talking about. So again here, we had this 4,000 psi after 3 days, more than 7,500 psi. That's often good just for standard weight concrete, and here we're getting it with semi-lightweight. I should point out that here we used standard sand, standard weight sand. It was just the coarse aggregate that was lightweight, but you can see here's the strength gain with time for different breaks. And as I said, the permeability can be very low, on the order of 10 to the minus 10 here, centimeters per second, as compared to something that might be 30 times higher for a normal strength concrete. So you can have, and in more extreme cases, you can have 100 times or more lower permeability, because the lightweight aggregate is slightly pozzolanic. It will actually bind better to the cement binder, which reduces the permeability. Also, it's harder for bleed water to accumulate under a porous aggregate. So it's a proven fact. It also has very low chloride permeability, so there's this Coulomb test monitoring the flow. So we did this on our mix design, and this is a relatively low Coulomb count, 300. And this we achieved, normally I think our average mix design here is about 112 pounds per cubic foot wet, and then if it hydrates, it could dry out with time. It should absorb less moisture because it has low permeability, so its density shouldn't be changing. You can see that it's, for those who don't know, it's made, this is made from shale. So you put it in a kiln and it puffs up like Cocoa Puffs. So it's almost like volcanic pumice in that regard. It's got a nice surface here to stop it from absorbing too much water. So there was this big question about how are you going to prove that it had a 100-year service life. I did point out that there were 9 levels of quality control review, from the water district, the flood district, the division, the district, the headquarters, the Congress. So they all wanted to have proof. It wasn't just good enough. And they refused to allow you to use stainless steel rebar. They just said the contractor couldn't find it in the amount of time that was available. It had been planned to be a temporary structure. Now they want to make it permanent. And they wouldn't accept impressed current cathodic protection at the end. We have used passive anodic protect or anodes, as Birgit showed. We use that on the Diablo Canyon intake structure, where we put in zinc strips into the concrete, and that worked well there. But the contractor didn't want to do that here, so our options were getting more and more limited. So we did use these as it was showing. She was showing 75-year service life, and then she had to do something else after that. And so we didn't have all those options. So for whatever it was, we used this one model, which uses Fick's law for getting the chloride in and then predicting a certain amount of life. And that would get us out a long ways. Here, 100 years of exposure. You can see the cover that we had, 2 inches. You could add more cover, but then the thing wouldn't float. So we couldn't just add more cover to it. The core often goes up to 6 inches of cover, but that wasn't an option here. So as the chlorides are penetrating up to the steel rebar, it became an issue. So we also had to look at creep and shrinkage in our assessment to try to minimize construction joints and maintain also, it's not just the quality of the concrete, you have to consider the construction sequencing that goes on in here. So here's the mix design that we used to achieve this type of performance. We had fairly high cement content and fly ash as well. And this is the Stay-Lite. It's very good quality lightweight aggregate. The aggregate has for high strength concrete, you need to have good quality of lightweight aggregate. And Stay-Lite from North Carolina is some of the best in the country. We also had local sand and air entrainment, high-range water reducers. And this is more a controversial part, as we did use this DCI. It's a corrosion inhibitor. Normally Gerber doesn't do that, but to provide a belt and suspenders type of approach to this with so many levels of review and all questioning it and refusing to allow you to do anything in the future, it was an approach that managed to satisfy all the different reviews. So of course here you can see that we had lightweight coarse, sand, natural sand, some lightweight fines, and 20% cement here in this case, because heat of hydration is not an issue. Here's the good water cement ratio. We wanted to stay less than 0.4 to try to get the low permeability. I think the water cement ratio here, I probably went by it fast. It's 0.38, right, Richard? So this does show compressive strength as you get up here. We're at least over 7,000 psi with that water cement ratio, which exceeds the design criteria. So here's other influence on creep. So as your water cement ratio goes up, your creep goes up, so that's something you want to control. And you also want to get a good amount of aggregates in there to reduce shrinkage. But also the low water cement ratio reduces shrinkage as well. So again, we used the Stay-Lite lightweight aggregate. It is high quality. It's comparable with the strength of the cement. When it fractures right through the paste and the aggregate, whereas with standard weight often goes around it. So that means that there's less cracking. So even under operation, there'd be less cracking occurring, so less avenues for chlorides to get in. Well, I don't know about this thing about formed by volcanic ash, but this is used as shale that was expanded in the kiln. I think my person who helped me with this slide might have made a mistake, but it is light enough to float. So this is how the contractor was stockpiling it. He had to pre-soak it a little bit. And again, we did use air entrainment. It improves, decreases the permeability, decreases the bleeding. Here's a high-range water reducer to try to get around all the rebar. Low-range water reducer, try to extend its slump life so that all of the loss, often the high-range water reducers lose slump, and then this provides a backup at a good price. But also it has other advantages with regard to finishing with this admixture. Improves the concrete durability against freeze-thaw, this particular admixture. And here was the more controversial DCI. This is not arc corrosion, that's just representing the idea that it's important. It does allow you to make a certain numerical calculation about it counteracting so much chloride that's in there, so it was something that we could demonstrate to our clients. But again, we had to look a lot at the joint construction here. This is not our joint, but that's a typical problem where there's a water stop. And if you don't get the joints right, you can have corrosion happening that could lead to spalling. And to help provide a guarantee of that, on top of the water stop, we also have this Fuco injection, re-injection with a hydrophilic resin, to make sure and guarantee that there isn't a problem. So I believe at one place the contractor forgot the water stop, but he got the Fuco in there so we can inject it. So here's the Fuco lines going down the side and the water stop in the middle. And so often for offshore platforms, concrete gravity-based platforms, they just go with the injection piping, as it simplifies the construction issues. So this shows in a joint where you have the resin being injected. And this just gives you an idea that lightweight concrete is used for many different purposes. It can also be used with not just semi-lightweight like we have here, but you can use modified density concrete, so it's a little bit, or use some standard weight coarse aggregate and some coarse light that was used on the offshore platform here as a bridge. And